Alright, y'all, welcome back. I'm Mr. Boyden, your personal math teacher, and we're switching gears today, and we're going to talk about probability in our new probability unit. We're going to talk a little bit about randomness, quite a bit about probability, and a little bit about simulation. The first thing we're going to talk about is the law of large numbers. Now, the law of large numbers, the idea here is that if you had a small number of trials, then you could potentially get some really bizarre and strange results. Okay, and it's similar to the idea of sampling variability that we talked about in the previous unit. Okay, they're based on the same concept, in fact. Okay, but then if you had many trials, then your experimental probability is probably going to be pretty close to the actual probability. So let me give you an example with playing blackjack at a casino. That's going to be our first one. Okay, so if you go in and you play the optimal strategy for blackjack, you will win about 49% of the time. Okay, so you're going to lose more often than you're going to win, not by a lot, but just slightly. If you go in and you bet all your money and you play one hand, 49%, that's pretty close to a 50-50. And so you might double your money or you might be broke, but it's all going to happen at once. The law of large numbers is basically this idea that if instead of doing that, you went in and you played $1 at a time, over and over and over and over, you eventually, because you are in the long run, you're going to lose a little bit more often than you're going to win. Eventually, you're going to go broke. And this is how a casino makes money. Casinos do not like the idea of you coming in, for example, and if you laid down $1 million on the blackjack table. In fact, a lot of casinos won't even let you do that if you wanted to, because there's a huge risk for them if you do that. Even though they're more likely to win and it's more likely for you to lose, there's still a pretty darn good possibility at 49% that you could win and double your money and they would owe you $1 million. And casinos don't want to have to do that. So they want to encourage you to place many small bets. And then over time, they will win. Now, you could, well, not you, and I really want to discourage you from trying to do this, but there's a movie that came out about a decade ago called 21, and it was about I think it was at Harvard, if I remember. It was about a blackjack team. And it was this professor who was a really good at mathematics, and he taught his students how to do something called counting cards, and he'd fly them to Las Vegas on the weekend, and they would play blackjack all weekend long. Okay, and so with card counting, they got their win percentage up to about 51%. And you think, well, 51%, that's not that different than 49. It is if you're going to play hundreds and hundreds and hundreds and hundreds of hands. Because while it looks like a 2% difference, if you get to 51%, that means you're going to win more often than you lose. And so over the long term, over the long run, you will in fact make money. And that's what they did. They'd fly to Las Vegas, and that guy apparently had access to lots of money. So they'd take lots of money and they'd play for, a whole weekend, and they made millions and millions and millions of dollars. Okay, versus what happens on the other side is when people go play with a win rate of 49%, the casino makes millions and millions and millions of dollars. Okay, let's do another example. Let's talk about playing a sport against a player or a team that is much better than you. So my sub-example one is going to be with tennis, because that's a sport that I coach. And if you're playing a player that's way better than you, what's better for me? Playing only 1 point or playing a whole match? Okay, and which one takes more luck to win? If I'm playing against a player who's better than me, I've got a decent shot at beating that player on a single point. Now, it's less than 50%. I mean, it's maybe 30% or something like that. But it's possible that they could make a single mistake, or I could hit a really good serve, or I could hit one really good shot, and that's all it would take to beat them. Okay? But if I had to play a whole match, then if that player makes 1 or 2 mistakes, it doesn't really matter. They have a whole match for that fact that they're better than me to play out. Okay, and so for me, what would be better is if I could play only 1 point against a superior player. That's a much higher chance of me beating them, because weird things could happen. That's what I mean, like wonky results. That person could just make a mistake. If they make 1 mistake and we're playing only 1 point, I win. Okay, so that's why for me, playing 1 point would be better. You sometimes see this in team sports as well. In fact, I saw this in basketball when I was a little kid. That was before they had a shot clock in high school basketball. I saw a game where the underdog team, gets the ball and holds the ball for the last shot. Now, if you're not quite sure what that means, in high school basketball, the quarter is 8 minutes long. So like this team, they won the opening tip, and they kept the basketball for 8 minutes. Like they just dribbled around, and they didn't shoot. They didn't let the other team touch the ball. And so then the team that was the underdog, they got one shot at the end of that quarter. And then the next time they got the ball, they took one shot. And so what this did is this made it a game where basically each team gets the ball functionally, like, I think it was like 6 or 7 times. And so for the underdog to win, all they have to do is make a couple of those shots. Now, if they're a lesser team and they play against a good team and they play a style where they have to run up and down the court and each team gets the ball many times, they're going to get beaten very soundly. But by understanding that the law of large numbers would work against them because they had a disadvantage, they call it stretching the game out, but they basically say, we're not going to let you guys have the ball that much. We're going to keep the ball, and there's not going to be that many shots, and it's going to be like first team to 10 wins. Okay, so it sounds like a really weird strategy, but that coach is actually implying a really important probability concept, and that's the law of large numbers. That's pretty cool. I really thought that was a clever way to try to compete. Now, by the way, that underdog team did lose. Because the other team would steal the ball occasionally and go dunk it. So it didn't work out, but they did what they could to try to make it as fair a fight as possible, which is pretty cool. All right, let's do an example problem. And this one involves long run relative frequency. All right, Mr. Boyden randomly selects students and asks if they play Fortnite. The proportion which said yes is 37. Interpret the meaning of 0.37 as a long run relative frequency. Okay, long run relative frequency is kind of a new term, but it's getting at that idea with the law of large numbers that, like with the blackjack table, if you play many hands, you will win about 49% of those if you use an optimal strategy. Okay, so what does this mean here? This means if we ask many students if they play Fortnite, then we expect that about 37% of them will say yes. Okay, so on average, that's what would happen. All right, now another important question. If we select 100 students and ask them if they play Fortnite, do we know if 37 of them are going to say yes? Probably not. Okay, probably not 37 of them will say yes. Is it possible that 37 can say yes? Yeah, of course. In fact, it's the most likely thing, but 36 is likely, and 35, and 34, and 39, and all those, okay? So, will 37 of them say yes? Probably not, but maybe. It is important to understand that that's sort of like that non-deterministic language. Like we would think that about 37 of them would say yes, but perhaps it would be a different number, okay? So let's talk a little bit about simulation. Simulation is, at least in statistics or in probability theory, is when we try to imitate some sort of a chance behavior based on a model that is reflective of it. All right, that's probably not a very helpful definition, so let's get into it. In fact, these are probably not very useful examples, so let's do a real example. Let's say we know a guy named Steven, and Steven is a tennis player, and he makes 82% of his serves in tennis. We're going to describe a simulation method to simulate how many serves he makes out of 80. Now, we can often do this with a random number generator. Okay, so what I'm going to do is I'm going to generate random integers from, and in this case, to make it easy, I'm going to go from 1 to 100. And that way we can think of it, I'm making it out of 100 so it feels like percentages. Generate random integers from 1 to 100, and how many do I want? We're going to figure out how many serves he makes out of 80. So we're going to generate 80 random integers from 1 to 100. Numbers from 1 to 82, because he makes 82% of his serves, represent a made serve. Numbers from 83 to 100 represent a missed serve. Repeated numbers are still counted. So, because that's the idea, if like the number 52 is in the list more than one time, that's okay, because all it's doing, it's not representing a person, it's just telling us if it's a make or a miss. So repeated numbers will be counted. Okay. Now, we said up here in the definition, it said it's based on a model that reflects the situation. Model that reflects the situation. The known probability was 82. That's why we set this up so 82% of the numbers that were possible would represent a made serve. Okay, so repeated numbers will be counted. We will count up how many of the numbers out of 80 are a make or a made serve and record that number. Okay, so that's a simulation. And we could run that simulation over and over and over and over again. Ideally, we would write a computer program that would do it for us, so we don't have to count numbers from 1 to 80. That would get really old. But that's an example of how to simulate this. Okay, so your homework will sometimes ask a question in AP about, like, is your result surprising? And so what they're asking about is, like, when we look at the results of the simulation, does the thing that happened fall within the normal outcomes of the simulation? So let me give you an example down here. So let's say that on Tuesday, Stephen makes only 4 out of his first 10 serves. We want to know if this is surprising, and we're going to run a simulation of this. So I want to encourage you to pause the video real quick and just practice writing a simulation up for this. Okay, because there's an example up above. Try this one and then get some feedback. Okay, so what I would do, and if you haven't hit pause, you may want to do that now. So generate random integers from 1 to 100, where 1 through 82 represents a make. How many random integers do we want? We want 10, because in this case he's only doing 10 serves, not 80. So 10 random integers from 1 to 100, where 182 represents a make. Count the number... Count and record, I should say. Count and record the number of makes. Okay, now, guys, it gets a little boring if you have to sit here and watch me run that simulation, 10 times or whatever. But here's, I'm going to talk you through what would end up happening if we took the time to do that. We'd probably make a dot plot of this. So he could have made 10 serves, could have made 9, could have made 8, 7, 6, 5, 4, 3, 2, 1, or it'd be unusual, but he could have made 0. And so what's probably going to happen is you're going to have a few in here in the 8 range, and a few in the 9 range, maybe even a few in the 10 range. Maybe there's only 1 7, 2 6s, maybe no 5s and a 4. Now, or maybe a 5. So I'm kind of making this up, right? But this is possibly what could happen in the simulation. So they ask us, is this a surprising result? If this is your graph, you would say, well, in our simulation, the lowest number he made was 5. And so based on this, he made them from 5 to 10, and honestly, most of them were 8s and 9s. And so, yeah, it would be really surprising based on this if he suddenly went out in the real world and produced a data point down here. That would be unusual because that never happened in our simulation, and nothing that low, in fact, happened in our simulation. So would that be surprising? Yeah, we would say based on this, yes. Now again, guys, each data point on here represents you running this simulation and recording the number of makes. And so that's why I'm not actually showing that right now. That would take, I don't know, 15, 20 minutes, and I'm pretty sure you would shut the video off. So I'm going to spare you. Okay? So that's the deal on that. The last thing we're going to do today is an example around HIV testing. Okay, now, I do want to say that some of these numbers are a little bit outdated. These are a couple years out of date. I think it was around 2015 that those were true. I understand they've changed the methodology of HIV testing just a little bit since then with something called an ELISA test. But in any event, it illustrates a really important point that can come up just in the numbers of mathematics. It's kind of weird. And then additionally to that, especially if you're going to do anything with science or medicine, it's important to understand that there are some really weird things that can happen in measuring and testing, and this example should illustrate that. Okay, so up at the top we have some facts, down below we have some questions. All right, so the facts. The false negative rate for an HIV test according to the National Institutes of Health is 0.01. That's 1%. Okay. Now, false negative, what that means is you get a negative test result, which says you don't have HIV, even though you actually do have HIV. Next fact, the false positive rate, meaning that it says it has a test positive saying it detected HIV, even though you do not have HIV, is 0.004. And as of 2019, about 0.3% of all Americans have HIV. And then finally, when a person tests positive, a provider will typically run an additional test just to confirm it and make sure. Okay, and if you got like a positive and then a negative, you go, oh, wait a minute, we got to start over and think carefully here and figure out what's going on. Okay, so then we have some questions down below. What proportion of people who take an HIV antibody test will have a positive result? And then the questions go from there. So one of the things that's really challenging here is it's pretty hard to just look at these numbers and answer a question like what proportion of people who take a test will test positive. Hard to think about. So we need a way of organizing the information. And the method that I'm going to show you today for organizing this is called a tree diagram. Okay, so let's write that out. A tree diagram. Okay, and so it's going to start out like this. We're going to start out with people. Now, we have some people who are HIV positive, and then we have people who are HIV negative. According to this scenario, it says about 0.3% of all Americans have HIV. That's what we mean by HIV positive. So that would be 0.003. That's how we would write that as a decimal. Remember, 0.03 is 3%. So 0.003 would be 0.3%. And what that means, we got to consider the complementary probability. That means about 99.7% of people would test or are HIV negative. So 0.997. Okay, so that encompasses that first piece of information. Now, they give us information about the false negative rate. Remember, that means a person has HIV, but they test negative. So you could test, so this is, I should label this out. This is your HIV status, this column, and this is your test result in this column, or a person's test result, not yours. Okay, you're not taking a test today. So test result. So a person who has HIV would take an HIV test, and they could test positive, or they could test negative. According to the facts over here, the false negative rate is 0.01. That's 1%. So false negative, that's this one right here. And that means if a person with HIV would test negative 1% of the time, it means they would test positive 99% of the time. That's just the complementary probability. 99% and 1% add up to 100, right? Now, if you're HIV negative, you could test positive, that happens, and you could test negative, and that happens more frequently. How frequently? Well, they said the false positive rate, meaning you test positive even though you shouldn't have, is 0.004, which means that this rate down here is 0.996. And guys, again, it's just if you're HIV negative, those are the two things that could happen, so those two probabilities have to add up to 1. Okay, so that's a complete tree diagram. Now, the tree diagram doesn't answer the question on its own, but what it does is it lays out all the possibilities of things that could happen, and it'll give us an idea of how to do the mathematics to answer these questions. So let's try to use that tree diagram now to answer the question at hand. What proportion of people who take an HIV antibody test will have a positive result? So what we're going to do is we're going to look at the table. A positive result, that's a test result. Positive test result is here and there. So it's asking us what proportion or what percentage of the people in the country would, if they all took a test, would fall into one of those two categories. So here's how we figure that out. We're going to find these end branch probabilities. And so what we do, to find out the probability of being this person, we start with all the people and we just trace along the branch. So that person would be HIV positive, and they would have a positive test result. What's the probability of that? It's these two numbers on the branch multiplied together. So that's how I'm going to get this next number, 0.003 multiplied by 0.99, and that is, looks like 0.00297. Okay, I'm going to repeat the same thing down here for this spot. So 0.997 multiplied by 0.004. And that is, looks like it's 0.00398. 0.88. So we just calculated two probabilities of two different ways that a person could have a positive HIV test. It could be that they have HIV and tested positive, or it could be that they do not have HIV and they tested HIV positive. So how do we find the probability that a person will have a positive test result? Well, we add those two together, 0.00297 plus 0.003988. Let's do just a little bit of addition. And what I got when I did that was 0.006958. Now, guys, they asked for the proportion, so I've given that. I'm also going to write the percentage because for a lot of us it's easier to think about. That's 0.6958%. And already that should be a little bit shocking because we know that only about 0.3% of Americans have HIV, and yet almost 0.7% will test positive. Okay, that's more than double. Oh, now they're still a small number, but that's still more than double, so that's kind of scary. Let's do the next question. If a person received a positive test result, okay, so pause. Because you see how we're talking about these same people who had a positive test result? What is the probability that they actually have HIV? So the people who received a positive test result, that's out of those people, 0.00698. And it's saying, this is a conditional probability. It's saying out of those people, what is the probability that they actually have HIV? That's these folks, okay, who tested positive and actually have HIV. I'm going to erase those because they look like minuses. So that's 0.00297. Okay, and so we just need to divide those two in the calculator. Now, dividing is not hard. The setup is the hard part, but 0.00297 divided by 0.006958. Okay, and when I did that, I got 0.42. I'm going to round it. 0.427. Now, that's interesting. So, guys, if you, and this is something, especially like when you go to college. I know when I was in college, it was a big push. Like they really want everyone to get tested for stuff like this all the time. And just because you're in college and, well, they want you to get tested. Let's leave it at that. But it's very interesting that if you go and you get a positive test result, according to this, it's actually more likely that you do not have HIV than if you do, which is bizarre. Isn't that bizarre? Because you up here you see, wait, but they're pretty darn accurate tests. I mean, up here at the top, 1% false rate and 0.4% false rate. But because there's so few people, proportionally speaking at least, who actually have HIV, it leads to this weird. Isn't that just so strange? Such a strange result that there's only a 42% chance. And guys, the math is right. I didn't mess it up. That truly is what it is. Okay. Now let's do the same thing in the opposite direction. If a person received a negative test result, what is the probability that they do not have HIV? Now, guys, I want to encourage you to stop the video and try this one. It's similar to what we just did, but it would give you a chance to kind of test your skills. So I want to encourage you to pause because I'm going to start it right now. So what I'm going to need in order to do this, I'm going to need some more probabilities on the table. I'm going to have to finish out the ends of those branches. And so I'm going to type in like 0.01 times 0.003. And so that is 0.00003. And I'm also going to need this probability down here, so 0.997 times 0.996, and I get 0.993012. Okay, so let's try to answer this question. If a person received a negative test result, okay, so guys, they're only talking about people who got a negative result. Now, who are those people? Those are, let's do color coding, but with a new color. Let's do yellow. These are our negative test result people. So we need to add those two together. And that's what I'm going to do. So I'm going to, wow, that's not going to change very much. So 0.99, this is funny. So we're going to take that answer, we're going to add 0.00003. And the number I get for that is, where's my pen? 0.993042. And they asked, out of those people, what's the probability they do not have HIV? So HIV negative, Negative test, so this number is going to go on top, 0.993012. All right, let's type that in. So 0.993012 divided by that previous answer. And I, this is pretty darn sure, 0.99997. Okay, 0.99997. So what does that mean? That means that if you had a negative test, you could be 99.997% certain, or there's a 99.997% probability that you do not have HIV. That is a correct test result. So isn't that weird? Like a positive test, you really don't know much. I mean, knowing 42% certainty, you really don't know much. If you get a negative test result, it's not 100% guarantee, but you pretty well know. Okay, now maybe this makes that final fact make a little more sense. That right here where it says, when a person tests positive, a provider will typically run a second test. It didn't say when they tested negative, it would run a second test. Because if it tests negative, you're pretty darn sure that it's right. If it tests positive, you better test that again. Okay, we're not really sure. We don't want to start a treatment, for example, on someone when we're 42% sure, 43% sure that they have a condition. Okay, two more things. As of 2009, this is a fact taken from the CDC, as of 2009, 82.9 million people had been tested for HIV in the United States. And we want to know what are the number of false positives and false negatives. Okay, so false positives. Where are our false positives? Our false positive is right here. So our false positives, how many would we have? Oops, I don't know why I put a 5. I meant to put an F. False positives, that would be 82.9 million people. And that's how you're 82.9 million, by the way, multiplied by that probability. So false positive 0.003988. Okay, so let's type those in. 82,900 times 0.003988. Let's see. That is 330,605 people. That's how many people got a false positive. Now let's do the same thing for a false negative. And if that made sense to you, you might want to pause the video and try that calculation. What I'm going to do is I'm going to take that 82.9 million number and I'm going to multiply it by the false negative rate, which is this one up here. So 0.00003. Okay, and that number is much smaller, which makes sense. That's a much smaller decimal. So 2,487 people got a false negative test result. Okay, so isn't that interesting too? False positive here. A lot of people getting a false positive, not as many people getting a false negative. Now, understand that in medicine, they can change the way these tests work. They can make them more sensitive, so they're more likely to have a positive test, or they could make them more specific, so they're less likely to have a positive test. And the researchers do this on purpose, so let's talk about why that is, and why would they do this? And look, it's sad that 330,000 or 331,000 people at one point were walking around thinking they had HIV when they didn't. I'm sure that was really stressful. And then there were also a handful of people that had a false negative, which means they had HIV, but were walking around not knowing that they had it, even though they'd been tested and done everything right. So here's the question at the bottom. What's more costly, a false positive or a false negative? Now, costly is in quotes, because when I say costly, I'm not talking about money, okay? Guys, certain mistakes are super costly. If you don't see the light turn red when you're driving and you keep going, that's a costly mistake, okay? It's not about money. It's a really costly mistake. That's a big deal. If you, I don't know, forget to turn off the stove, but you're still standing there, that's not a very costly mistake, right? So what's more costly, a false positive or a false negative? And I want you to think about it both for the individual and for society. Which of those do we really, really want to avoid, as both as individuals and as a society? So, and there is a correct answer on this one. And both are bad. Both stink, okay? But the one that really, really, really is horrible is a false negative, okay? Because if you get a false positive, What happens is you take another test and you probably figure out the truth. The very worst case scenario of a false positive is you have a lot of stress, which is bad, and that you potentially end up taking some drugs that you don't need, and it costs money. And look, that's a terrible situation. But consider what happens in the case of a false negative. A person who gets a false negative then does not get treatment, and their disease continues to progress, typically to a point, or often to a point, where they can't be saved or they can't live a full life. Additionally, in that time, since they don't know that they're HIV positive, they could potentially be infecting other people without knowing it. That could potentially happen. And so both on an individual level and on a societal level, a false negative is very, very costly. It's something that we can't really afford. And so when you look at these numbers over here, that's why they are the way they are. A false positive it leads to a result, and you have all these false positives, and it's a bummer, but it's not the end of the world. A false negative is horrific, and you know what? 2,500 people, that's way too many. That's stinky, and they have improved the test since I pulled these facts, which is awesome. But look at the relative sizes. This is less than 100. This less than 100th of the 330,000. So when they develop these tests, they're very intentional because they understand statistics and probability. They're very intentional about how they design them, and they're thinking in mind down here of what would be more costly to us. What's worse, having a false positive or false negative? And in my opinion, they got that answer right with these numbers and with their testing. Okay, so that's something to keep in mind. As I'm recording this video, we're in the middle of the COVID-19 pandemic, although it's almost 2021 now. So is it going to be called COVID-21 pretty soon? No, I don't think so. But in any event, there's been a variety of different tests, and some of them have a really high false negative rate. And there's a trade-off because they come back faster, but you end up sending people out with these false negatives, and they think they're not going to infect other people, and they do. So it's always tricky. For most of these things, there's not a perfect test in medicine. And so it's a really delicate balance, weighing out the costs of this versus the costs of that, and how expensive it is to run the test, and how long it takes to get the results back. Because like with COVID, for example, if it takes a week to get the test back, it's not very helpful. Although if the false negative rate's 50%, that's not very helpful either. So in any event, that's the probability of this stuff, and a little intro to sort of medical testing at the same time. Maybe that's something that'll interest you in your future, and you'll get to be solving the problems of the world and employing a few of the things that I've taught you. That would be pretty cool. Hopefully you enjoyed that. Hopefully you enjoyed the rest of the video as well. I really appreciate you sticking around and seeing the end of it. And I'll see you next time.